Welcome to Chapter 9 on Magnetic Particle Testing, or MT. In this chapter we are going to treat MT as an inspection discipline rather than simply as a technique for putting magnetic powder on a component. The objective is to understand why the method works, what conditions are necessary for reliable detection, how to choose the correct magnetizing technique, and how to control the process so that the indication you see can be trusted. The course is aimed at Level 2 and Level 3 personnel, as well as engineers and inspectors who need a practical understanding of magnetic particle examination. We will begin with the advantages and limitations of the method, then build the physics from magnetic materials and flux fields. From there we will move into current types, direct and indirect magnetization, equipment, particles, lighting, the inspection sequence, evaluation, demagnetization, and quality control. The later sections then apply those principles to welds, oil and gas equipment, calculations, examinations, and field decisions. Keep one principle in mind throughout the chapter: MT detects a magnetic response, it does not directly see a crack. The discontinuity changes the magnetic field, and the particles reveal that change. Once that relationship is clear, the rest of the method becomes much easier to understand. Before we discuss equipment or calculations, it is useful to see the complete learning path. Magnetic particle testing starts with material suitability. If the component cannot be magnetized effectively, MT is not the correct method. Next, we need to understand how a magnetic field behaves inside the component and what happens when a discontinuity interrupts that field. The third stage is magnetization. The choice between alternating current, half-wave rectified current, full-wave current, direct induction, a yoke, a coil, prods, or a central bar conductor is not arbitrary. Each produces a different field condition. Then we introduce particles and interpret the pattern they form. Finally, process quality controls, demagnetization, cleaning, documentation, and acceptance criteria determine whether the examination is complete and defensible. This sequence is important in the field. A common mistake is to start with whatever equipment is available and then try to make the inspection fit the equipment. A professional inspector does the opposite: identify the expected discontinuity, determine the required field direction and depth capability, and then select a technique that can provide it. That decision-making approach will be used throughout this chapter. Let us start with the fundamental question: what is magnetic particle testing? MT is a non-destructive examination method used primarily to locate surface and near-surface discontinuities in ferromagnetic materials. The word ferromagnetic is critical. Materials such as iron, many steels, cobalt, nickel, and suitable 400 series stainless steels can support a strong magnetic field. Materials such as aluminum and copper cannot be examined effectively by conventional MT simply because they do not develop the required magnetic response. The inspection principle is a sequence of cause and effect. First, we establish a magnetic field in the component. If the material contains a discontinuity that interrupts the preferred magnetic path, the magnetic field is disturbed. Some of the magnetic flux leaves the surface locally. That external field is called flux leakage. Magnetic particles placed over the area are attracted to the leakage field and form a visible pattern. There are two familiar presentation modes. Visible particles are selected to contrast with the surface and are evaluated under suitable white light. Fluorescent particles emit visible light when excited by UVA, normally around the 365 nanometer region, giving a high contrast indication in a properly darkened inspection area. Notice the important distinction: the particles do not chemically react with the crack. They respond to magnetism. That is why field direction, magnetizing strength, particle properties, lighting, and surface condition all directly influence sensitivity. Now consider why MT is so widely used in maintenance and fabrication inspection. Its major strength is the ability to produce an indication directly on the component while the examination is taking place. When the technique is properly selected, a surface-breaking crack can appear as a sharp, easily interpreted particle accumulation. MT is also practical on irregular shapes. A weld attachment, shaft, flange, casting, or complicated forged component does not necessarily need to be machined into a simple geometry before it can be inspected. Portable yokes and other equipment can be taken directly to the work site, which is particularly valuable during plant shutdowns. Another advantage is speed. Compared with methods that require significant processing or interpretation time, MT can provide immediate visual feedback. That makes it useful for screening large numbers of welds or components and for checking repair areas before the equipment returns to service. However, an experienced inspector does not confuse convenience with unlimited capability. MT is strongest for surface and near-surface discontinuities in suitable ferromagnetic materials. The method gives an indication of size, shape, and location, but the indication still has to be classified and evaluated against the applicable acceptance criteria. A strong indication is not automatically a reject, and a weak background pattern is not automatically harmless. The practical value of MT therefore comes from combining rapid detection with disciplined technique selection and evaluation. Magnetic particle testing, or MPT, offers several important advantages, which make it one of the most widely used NDT methods for detecting surface and near-surface discontinuities. First, MPT is highly effective for detecting surface and near-surface defects such as cracks, lack of fusion, lapse, and other discontinuities in ferromagnetic materials. Another major advantage is its ability to inspect components with irregular or complex shapes. Unlike some inspection methods, the component geometry does not necessarily need to be simple or uniform. MPT also offers versatile equipment options. Depending on the application, equipment can be stationary, portable, or even automated, making the method suitable for both workshop and field inspections. The equipment and operating costs are relatively low, which makes magnetic particle testing an economical NDT method for many applications. One of the biggest advantages is that MPT provides immediate results. When magnetic particles accumulate at a leakage field caused by a discontinuity, the indication can be observed directly on the component surface. MPT can also provide an approximate indication of the size, shape, orientation, and location of a discontinuity. This information helps the inspector evaluate and assess the indication. Finally, compared with some other NDT methods, surface preparation requirements are generally less critical, although the surface must still be clean enough to allow proper magnetization and reliable interpretation of indications. So, in summary, magnetic particle testing is fast, economical, versatile, and highly sensitive to surface and near-surface discontinuities in ferromagnetic materials. The limitations of MT are just as important as its advantages. The first limitation is material. If the component is non-ferromagnetic, conventional magnetic particle examination is not the appropriate method. This is why material identification is an early step in the inspection process. The second limitation is coating. A thin, qualified coating may sometimes be inspected through, depending on the governing procedure and demonstrated sensitivity. Thick paint, plating, corrosion products, or other layers can increase the distance between the discontinuity and the particles and can reduce the effective response. Never assume that a painted surface is acceptable simply because particles still move. The third limitation is orientation. A magnetic field has a direction. A discontinuity is most effectively detected when the field crosses the discontinuity approximately at right angles. If a crack runs parallel to the field, it may produce little useful leakage and can be missed. This is the reason professional procedures normally require examination in at least two directions approximately 90 degrees apart. Finally, MT is a controlled process. Particle concentration, lighting, equipment output, magnetizing technique, surface condition, and demagnetization all matter. The most dangerous MT mistake is often not a visible equipment failure, it is a technically incorrect setup that produces a convincing but incomplete result. So, when you see a statement that MT is fast and inexpensive, remember the qualification: it is fast and effective when the material, field direction, current type, and process controls are appropriate. To understand why some materials are suitable for MT, we need to introduce magnetic permeability. Permeability describes how readily a material supports magnetic flux compared with the surrounding medium. Diamagnetic materials have permeability slightly below that of air and are weakly repelled by magnetic fields. Ferromagnetic materials have permeability slightly above that of air, but they do not retain useful magnetism after the external field is removed. These categories are not suitable for conventional MT. Ferromagnetic materials behave very differently. Their permeability can be much higher, they are strongly attracted to magnetic fields, and they can retain residual magnetism. This combination makes them suitable for establishing the magnetic circuit required for MT. The presentation also points out the effect of temperature. As temperature changes, magnetic properties change. At the Curie temperature, the ferromagnetic behavior is lost. In practical inspection work, that means temperature should not be ignored when a component is being examined hot or when a procedure specifies a maximum examination temperature. One useful distinction is permeability versus retentivity. Permeability relates to how readily a material becomes magnetized. Retentivity relates to how much magnetism remains after the magnetizing force is removed. Those properties influence whether continuous or residual magnetization can be used. For an inspector, the lesson is simple: material behavior controls technique selection. Do not treat all steels as magnetically identical. The magnetic domain model gives us a physical picture of what happens inside a ferromagnetic material. In a ferromagnetic material, microscopic magnetic regions called domains exist. Each domain behaves like a tiny magnetic region, but in an unmagnetized component the domains are oriented in many different directions. Their effects largely cancel, so the component has little net external magnetism. When we apply an external magnetic field, domains begin to align with that field. As the magnetizing force increases, more domains participate in the alignment. Eventually the material approaches magnetic saturation, where most of the useful domain alignment has already been achieved. This model explains why magnetization is not simply an on or off condition. There is a progression from weak magnetization through increasing alignment toward saturation. It also explains why excessive current is not automatically better. Once the useful magnetic response is established, adding substantially more magnetizing force may produce little additional benefit while increasing heating or other practical problems. The domain concept also helps explain residual magnetism. When the external field is removed, some domain alignment can remain. The amount retained depends on the material and its magnetic characteristics. When you later study hysteresis, think back to this slide. The hysteresis loop is essentially a graphical way of describing how the material responds as the magnetizing force increases, decreases, reverses, and is removed. Now we can connect the domain behavior to the actual MT indication. Magnetic flux can be represented by lines of force. These lines form continuous paths through and around the magnetic circuit, and they become denser where the magnetic field is stronger. A sound, uniformly magnetized section provides a relatively continuous magnetic path. Introduce a crack, seam, or other discontinuity and the magnetic path is disturbed. The field must spread around the interruption, and part of the flux crosses the component surface. This local external field is flux leakage. That leakage field is what attracts the particles. At the edges of a discontinuity, the field behaves as though localized magnetic poles have been created. The particles gather there and produce the indication that the inspector sees. This gives us the most important geometric rule in MT. The strongest useful indication normally occurs when the magnetic field is approximately perpendicular to the discontinuity. If the field is parallel to the discontinuity, leakage can be weak and the indication may disappear. Imagine a long crack running north to south. A north-to-south magnetic field gives poor crossing of the crack. Rotate the field 90 degrees and the field now crosses the crack, increasing the leakage response. This is why two-direction inspection is not just a procedural habit. It follows directly from the physics of flux leakage. The hysteresis loop is the next step in understanding magnetization and demagnetization. On the horizontal axis we consider magnetizing force, and on the vertical axis magnetic response or flux density. Starting from a demagnetized condition, increasing the applied field moves the material toward saturation. If the magnetizing force is then reduced to zero, the material may still retain magnetism. The amount remaining is associated with retentivity, or residual magnetism. To remove that residual magnetism, an opposing magnetizing force is required. The magnitude of that reverse force is associated with coercivity. This distinction matters in practical MT. A material with low retentivity may not hold enough magnetism for a residual examination. That is why the continuous technique is important for low retentivity materials. Conversely, a component with substantial residual magnetism may require a deliberate demagnetization procedure before welding, machining, or service. The loop also helps explain the difference between soft and hard magnetic materials. Soft magnetic materials tend to have a narrower loop and are easier to magnetize and demagnetize. Harder magnetic materials tend to retain more magnetism and resist demagnetization. For examination purposes, remember the relationship rather than memorizing isolated words. Saturation describes the highly magnetized condition, retentivity describes what remains, and coercivity describes the reverse force needed to remove it. The type of magnetizing current strongly influences MT performance. The comparison on this slide is really a comparison of three things: penetration, particle mobility, and demagnetization behavior. Alternating current is strongly surface-oriented because of the skin effect. It is excellent for surface breaking discontinuities and provides good particle mobility, but it should not be treated as a general-purpose deep inspection current. Half-wave rectified current provides strong pulsing. That pulsing gives excellent particle mobility, which is particularly useful in dry powder applications. Unlike simple AC, it can provide a more useful response for near-surface discontinuities. Its major disadvantage is that it does not provide effective directional reversal for conventional demagnetization. Full-wave rectified current gives a pulsating direct current type of magnetic field and can provide good penetration. Depending on the equipment, it can also be used for demagnetization. Three-phase full-wave systems are commonly associated with larger stationary equipment. The key is not to memorize AC equals good or DC equals bad. Instead ask, what depth do I need to inspect? How much particle mobility do I need? Can the component retain magnetism? And how will I demagnetize it afterward? Those questions lead naturally to the detailed discussion of AC and rectified current. Alternating current reverses direction repeatedly. That changing field produces an important surface phenomenon called the skin effect. The alternating magnetic response is concentrated toward the surface, so the method is highly effective for detecting surface breaking discontinuities but is not the preferred technique for reliable subsurface detection. The same alternating behavior provides a useful particle mobility effect. Particles are continually influenced by the changing field, helping them migrate toward leakage sites. This can be especially helpful when inspecting a clean surface with suitable particles. AC also has a practical demagnetization advantage. Because the magnetic field reverses direction, a controlled reduction in AC can progressively reduce the net magnetization. However, the inspector must pay attention to coating limitations and procedure requirements. A coating can separate the particles from the leakage field and reduce sensitivity. Some specifications place explicit limits on inspection through plating or coating. A common mistake is to say that AC detects cracks without qualification. The technically correct statement is that AC is strongly suited to surface discontinuities. If the examination objective includes near-surface flaws, another current type may be required. In the field, the current choice should therefore be driven by the expected flaw depth, material behavior, surface condition, and governing procedure, not simply by whatever power source happens to be available. Half-wave and full-wave rectification are best understood by looking at what happens to the AC waveform. In half-wave rectification, one half of the AC cycle is suppressed. The result is a pulsating current that flows in one direction with pauses between pulses. Those strong pulses provide excellent particle mobility. That is why half-wave is commonly associated with dry powder MT and portable equipment. The method can provide useful penetration while keeping the equipment relatively simple. Its limitation is demagnetization. Without effective reversal of the magnetic field, it is difficult to progressively remove residual magnetism. Full-wave rectification treats the negative half-cycle differently. It is inverted so that the current continues in the same general direction, producing pulsating direct current. This provides good penetration and can be arranged to support demagnetization. Three-phase full-wave equipment distributes the electrical demand across 3 phases and is therefore well suited to high-capacity stationary benches. It is less portable and has higher initial equipment requirements, but it can provide a very versatile inspection system. When choosing between these systems, think in terms of the complete job. A portable weld inspection, a repetitive shaft inspection on a stationary bench, and a large forging examination may all require different electrical solutions even though the basic MT principle remains the same. There are 2 broad ways of establishing magnetism in a test object: direct induction and indirect induction. With direct induction, electrical current actually passes through the test component. A head shot is the classic example. The component is placed between the head and tailstock, current flows through it, and a circular magnetic field forms around the current path. Prods work on the same fundamental principle, with current entering and leaving the component through contact points. Direct induction can be very effective, but it creates an important safety and quality concern: arcing. If contact is poor, or if the component is moved while current is flowing, an arc can damage the surface. This is unacceptable on many finished or pressure-containing components. Indirect induction creates magnetism without passing inspection current directly through the test object. A yoke, rigid coil, or cable wrap can establish a longitudinal field. A central bar conductor can create a circular field in a surrounding ring or hollow component. The field direction determines the flaw orientation that will be best detected. This is why the terms direct and indirect should not be confused with circular and longitudinal. Direct induction normally produces a circular field, but indirect methods can produce either field depending on the arrangement. The final principle is critical: to cover different discontinuity orientations, inspect with magnetic fields in at least 2 approximately perpendicular directions. Let's make the field orientation rule practical. A circular magnetic field is produced when current passes through a component or through a central conductor arrangement that induces magnetism in the surrounding part. The flux forms closed loops around the current path. There are no simple north and south poles at the ends of a purely circular field. A circular field is therefore well suited to finding longitudinal discontinuities. If a crack runs along the axis of a shaft, the circular field crosses that crack and produces useful leakage. A longitudinal field is different. It runs generally along the length of the component and produces north and south pole regions at the ends. This field is well suited to detecting transverse discontinuities. The right-hand rule gives us a simple way to determine the circular field direction. Point the thumb of your right hand in the direction of conventional current flow. Your curled fingers indicate the direction of magnetic flux around the conductor. The important point is that equipment names are not enough. A yoke creates a longitudinal field. A head shot creates a circular field. A central bar conductor creates a circular field in the surrounding component. A coil creates a longitudinal field. If you remember only one relationship from this section, remember this: circular field for longitudinal flaws, longitudinal field for transverse flaws. The two are complementary, and that is why inspection direction must change. MT equipment ranges from large stationary benches to mobile power packs and small portable units. The choice is driven by component size, access, current requirement, production volume, and the required technique. A stationary wet bench offers the greatest versatility. It normally combines a low-voltage, high-current power source with head and tailstock arrangements, a coil, a particle tank, and controlled inspection lighting. This is ideal for repetitive examination of shafts, forgings, gears, and other components that can be brought to the workshop. Mobile units bring more capability to the work site. They can support cable wraps, coils, prods, clamps, and other techniques where the component cannot easily be transported. Portable units are optimized for accessibility. A yoke or small power source can be carried to a weld or structural component during a shutdown. The trade-off is lower current capacity and fewer available magnetizing configurations. An experienced inspector therefore does not ask, which machine is best. The better question is, which machine can establish the required magnetic field on this component, in the required direction, with adequate sensitivity and safe operation? Equipment capability must also be supported by process controls such as current verification, yoke performance checks, lighting checks, bath checks, and calibration or functional verification as required by the governing procedure. Prods and yokes are among the most familiar field MT accessories, but they create very different magnetic conditions. Prods are copper contact devices. Current passes directly into the component at one prod and leaves through the other, creating a circular magnetic field around the current path. As prod spacing increases, the useful field between the contacts decreases. That means spacing, current, contact quality, and coverage all have to be controlled. The major disadvantage is arcing. Prods should not be used where an arc could damage a finished surface, pressure boundary, plating, or other critical area. In oil and gas shutdown work, this is one reason electromagnetic yokes are commonly preferred for weld examination. A yoke works indirectly. Current flows through a coil around a magnetic core, and the resulting magnetic field is transferred through the yoke legs into the component. The field between the poles is longitudinal. That makes the yoke particularly useful for detecting transverse cracks in welds and plates. The deadweight test is an important performance check for electromagnetic yokes. It demonstrates that the yoke can generate the required lifting or magnetizing capability. The practical lesson is simple: prods provide direct circular magnetization but introduce arc risk, yokes provide indirect longitudinal magnetization and avoid direct electrical contact with the test piece. Magnetic particles are not simply a visual powder. Their physical properties are part of the sensitivity of the examination. In the wet method, particles are suspended in a liquid vehicle and transported across the component surface. This provides very good control and is particularly effective on smooth surfaces and stationary bench systems. In the dry method, powder is applied directly, often with a squeeze bulb, and the method is especially useful with portable equipment and strong pulsed fields. Visible particles are colored to contrast with the test surface. The correct color is therefore not a matter of preference, it should provide adequate visual contrast. Fluorescent particles are coated with fluorescent pigments and are designed to provide high visibility under suitable UVA illumination. Dual-use systems can support both visible and fluorescent inspection, where permitted by the procedure. Two particle properties are particularly important. High permeability allows a particle to respond strongly to a leakage field. Low retentivity prevents particles from becoming permanently magnetized and clumping together. Particle size also involves a trade-off. Fine particles can respond to weak leakage fields and therefore help reveal small discontinuities, but they can increase background if the surface or bath is not controlled. Larger particles are less sensitive to weak fields. So the best particle system is not simply the finest powder available. It is the system that provides the required sensitivity with controlled background for the surface, current, vehicle, and inspection environment. Fluorescent MT depends heavily on lighting control. The fluorescent particle system is excited by UVA radiation, and the emitted light must stand out against the surrounding environment. For the training values shown here, the UVA intensity at the test surface should be at least 1000 microwatts per square centimeter, while ambient white light should be kept at or below 20 lux. The inspector's eye should also be allowed to adapt to the darkened inspection area for at least 5 minutes. These controls are not administrative details. Human vision is extremely sensitive to contrast, and a weak fluorescent indication can be lost when ambient light is too high or the inspector has not adapted to the dark. The wet bath is another part of the system. Water-based vehicles normally require appropriate wetting agents, anti-foam control, and corrosion inhibition. The particle concentration must be maintained within the specified range. The presentation gives 0.1 to 0.4 ml per 100 ml for fluorescent particles and 1.2 to 2.4 ml per 100 ml for visible particles. Water-based systems are often preferred because they have low fire hazard and can form indications quickly. Oil-based vehicles may be selected where evaporation or the governing specification makes them more suitable. The practical message is that fluorescent MT is a controlled optical system as well as a magnetic system. Good magnetization with poor lighting is still a poor examination. Several accessories are used to verify different parts of the MT process, and they should not be confused. A field indicator provides a quick check of magnetic field presence or residual magnetism. It is useful after demagnetization, but it is not a substitute for every other verification tool. A pi gauge is primarily a field direction device. Its simulated discontinuities respond to the magnetic field and help the inspector establish whether the field is oriented appropriately. Because it is a technique-sensitive device, it should be used according to the applicable procedure or standard. A gaussmeter or teslameter uses a Hall effect probe to make a quantitative magnetic field measurement. This is particularly useful when a specified residual field limit must be demonstrated. The quantitative quality indicator, or QQI, is especially useful because it can demonstrate field direction and field strength in the same examination setup. The thin steel strip contains artificial indications and is placed according to the approved procedure. Think of these devices as answering different questions. Is magnetism present? Points toward a field indicator. How strong is the field? Points toward a gaussmeter. Which direction is the field? Points toward a pi gauge. Can I demonstrate both direction and adequate strength? Points toward a QQI when the procedure calls for it. Good inspection practice uses the correct tool for the parameter being controlled. The 5-step MT process gives us a disciplined field workflow. Step 1 is to evaluate the material and the expected discontinuity. Step 2 is to select equipment and materials. Step 3 is to establish the inspection technique, including current type, field direction, and continuous or residual magnetization. Step 4 is to evaluate and document the indications. Step 5 is to demagnetize and clean when required. The important point is that these steps are connected. If you misunderstand the expected discontinuity in Step 1, you may choose the wrong field direction in Step 3. If you select the wrong particle system, evaluation in Step 4 becomes unreliable. If you ignore demagnetization, the inspection can interfere with the next manufacturing operation. The written work instruction is therefore critical. The Level 3 or responsible technical authority establishes the essential variables and inspection parameters. The Level 2 inspector then performs the examination within those approved limits. In the field, do not start by switching on the machine. Start by asking, what material am I examining? What discontinuity am I looking for? Where is it likely to be? What field direction will reveal it? What current type and particle system are required? What process checks must be completed? That sequence turns MT from a simple hands-on activity into a controlled non-destructive examination process. The first practical step is to evaluate the component before magnetizing it. Begin with material suitability. A quick magnet check can provide an initial indication that the component is strongly magnetic, but formal material identification should be used where required. Next, look at the surface. Paint, plating, corrosion, oil, scale, and other contamination can affect particle movement and indication formation. Bare, reasonably smooth metal normally provides the most reliable response. Geometry also matters. Threads, sharp corners, holes, keyways, press fits, and abrupt changes in section can create legitimate magnetic leakage unrelated to a damaging discontinuity. The inspector needs to recognize these conditions before interpreting an indication. Then consider the expected flaw. Manufacturing history, service history, stress conditions, weld configuration, accessibility, and likely crack orientation all influence technique selection. Finally, consider material magnetic properties. High permeability generally makes magnetization easier, while retentivity influences whether a residual technique is practical. An experienced inspector spends time looking at the component before touching the equipment. That short assessment can prevent a long inspection performed with the wrong technique. The objective is not simply to produce particles on the surface, it is to create a magnetic condition in which the expected discontinuity has a strong opportunity to reveal itself. Continuous and residual magnetization are fundamentally different inspection techniques. In the continuous technique, the magnetizing force remains applied while particles are introduced. Because the magnetic field is present at the time the particles migrate, flux leakage is at its useful maximum. This normally gives the highest sensitivity and is particularly important for materials with low retentivity. In a wet continuous examination, the component is flooded with the particle suspension, the flow is controlled, and the current is applied according to the procedure. The presentation uses rapid repeated current application and a minimum drain period to allow indications to form and excess liquid to leave the surface. The exact sequence and timing must always follow the approved procedure. The dry continuous technique works on the same principle. Particles are applied while the magnetizing force is active. In residual magnetization, the current is stopped before particles are applied. The particles are attracted only by the magnetism that remains in the component. This means the component must have sufficient retentivity to hold the field long enough for the indication to form. Residual examination can be useful in controlled automated applications, but it is not a universal shortcut. A low retentivity material may simply lose the field before the particles can respond. Remember the distinction: continuous means field and particle application occur together, residual means the field is removed before particle application. Finding a particle pattern is only the beginning of evaluation. The inspector must determine what the indication represents. A real discontinuity can produce a relevant indication. Cracks often appear as sharp, linear patterns because the magnetic leakage follows the crack geometry. Near-surface discontinuities can produce broader or less sharply defined patterns because the leakage field is weaker and spreads before reaching the surface. Visible indications are evaluated under suitable white light conditions. Fluorescent indications require controlled ambient light, UVA intensity, and dark adaptation. Evaluation should consider more than length. Look at the indication's shape, location, orientation, grouping, and distribution. A linear indication at a weld toe has a very different significance from a rounded particle accumulation at a sharp geometric corner. Documentation is part of technical evaluation. The report should identify the specification or procedure, technique, equipment, inspector, component, examination result, and relevant indication dimensions and location. A sketch or photograph can make the record much more useful. Most importantly, separate indication evaluation from acceptance. MT tells you that an indication exists and provides information about it. The applicable code, specification, drawing, or engineering requirement determines whether that indication is acceptable. Never invent an acceptance limit simply because an indication looks serious. Demagnetization is sometimes treated as the final button to press, but it has important engineering consequences. Residual magnetism can attract chips during machining, interfere with instruments, influence welding through arc blow, and contribute to unwanted particle attraction in machinery. Several demagnetization methods are shown. Small components may be passed through an AC coil while the field is gradually reduced. A component can also be placed in a coil or cable wrap and the current reduced progressively. With suitable equipment, a yoke can be withdrawn from the component while energized. Stationary benches often have a controlled demagnetization function. Heating to the Curie temperature can remove ferromagnetic behavior, but this is a major thermal operation and is not a casual field technique. Component metallurgy, dimensional stability, heat treatment, and service requirements must all be considered. For the values presented in this training, the residual field target is below 3 Gauss, or 0.3 millitesla, and the result should be verified with an appropriate field meter. The sequence is also important. Circular magnetism should be addressed before longitudinal magnetism. A standard field meter is not a universal detector of every magnetic condition, so technique and verification must follow the applicable procedure. Finally, clean the component. Leaving particle suspension or residue on a component after examination can create its own problems. Quality control is what turns an MT procedure into a repeatable inspection system. The first question is not, did the inspector see an indication, but was the inspection system capable of producing a reliable indication? A standard steel ring with artificial holes can be used to challenge a wet bench at specified current settings. This verifies that the system can reveal known discontinuities under controlled conditions. Bath quality is equally important. Water-based suspensions require suitable wetting and corrosion control chemistry. The system must be monitored so the fluid behaves consistently from shift to shift. For yokes, the dead weight test provides a practical demonstration of magnetizing capability. Lighting checks confirm that fluorescent examinations have adequate UVA intensity and controlled ambient white light. The ammeter must also be trustworthy. If the display says a certain current is flowing but the actual output is different, a carefully written technique can still produce an incorrect examination. Finally, the particle concentration is controlled by the settling test. This prevents the bath from becoming too weak to reveal small flaws or too strong to interpret clearly. Each control addresses a different failure mode. Passing the yoke test does not prove the bath concentration is correct. Passing the lighting check does not prove the current is correct. MT quality comes from controlling the complete system. The settling test is one of the simplest but most important controls for a wet MT system. Its purpose is to verify the concentration of magnetic particles in the suspension. The test is performed before use and at the frequency required by the governing procedure. The training material identifies daily testing and an additional check after 8 hours of continuous operation. The sample is allowed to settle in a graduated centrifuge tube, and the particle layer is compared with the specified concentration range. For the values in this presentation, fluorescent particles are controlled at 0.1 to 0.4 milliliters per 100 milliliters, while visible particles are controlled at 1.2 to 2.4 milliliters per 100 milliliters. Too little concentration is a sensitivity problem. There may simply not be enough particles to build a clear indication at a weak leakage field. Too much concentration is also a problem because excess particles can produce background and mask a genuine indication. The background fluorescence check provides another useful warning. Ideally, the particle layer should fluoresce rather than the entire liquid column. Fluorescence throughout the liquid can indicate bath breakdown, pigment stripping, or very fine particles remaining suspended. The professional mindset is to treat bath condition as a measurement variable, not as a visual guess. If the bath is outside the specified range, correct it before relying on the examination results. This slide gathers several high-value examination concepts. The first is the skin effect. Alternating current concentrates the magnetic response near the surface, making AC highly effective for surface discontinuities but unsuitable as the sole basis for reliable subsurface detection. The second is the continuous technique. Because the magnetizing force remains present while particles are applied, it normally provides higher sensitivity than a residual examination. The third is field direction. A yoke creates a longitudinal field, while a central bar conductor creates a circular field in the surrounding component. Confusing these two is one of the most common MT examination errors. The fourth is demagnetization. For the training values shown here, residual magnetism should be reduced below 3 Gauss, or 0.3 millitesla. The QQI is another common examination point because it can demonstrate both field direction and field strength. A field indicator and a pi gauge answer narrower questions. Finally, the settling test concentration for fluorescent particles is 0.1 to 0.4 milliliters per 100 milliliters in this training material. Do not memorize these as unrelated facts. Connect each one to its purpose. That makes the information easier to remember and, more importantly, easier to apply correctly in the field. The first mock quiz section is designed to test whether you can apply the principles rather than simply recognize terminology. For the first question, the advantage of MT is its ability to reveal surface and near-surface discontinuities in suitable ferromagnetic material. The other choices violate the basic limitations of the method. The second question tests the skin effect. Alternating current is the current type associated with strong surface concentration. The third question tests induction technique. A central bar conductor is the indirect arrangement that creates a circular magnetic field in the surrounding component. The fourth question tests process control. The settling test is used to verify magnetic particle concentration in the suspension. When using these questions in a classroom or YouTube course, do not stop at the correct letter. Ask yourself why the other choices are wrong. For example, the fact that PT can inspect non-ferromagnetic material does not make it an MT advantage. Likewise, equipment agitation and vehicle fluorescence are different control issues from particle concentration. That habit, explaining both the correct answer and the reason the alternatives are wrong, is one of the best ways to prepare for a professional Level 2 or Level 3 examination. This review section tests several concepts that often distinguish basic memorization from real understanding. First, the magnetic field should cross a surface discontinuity approximately at 90 degrees for maximum useful flux leakage. If the field is parallel to the discontinuity, the leakage may be weak. Second, fluorescent particles provide excellent visual contrast when the UVA and ambient light conditions are properly controlled. The presentation identifies green-yellow fluorescent response as particularly visible. Third, MT particles should have high permeability so they are readily attracted to leakage fields, but low retentivity so they do not retain magnetism and clump together. Magnetic writing is an important false indication example. It can occur when a component is accidentally magnetized through contact or handling and produces a particle pattern that resembles a real discontinuity. The correct response is investigation and re-examination, not automatic rejection. Finally, the yoke creates a longitudinal field. If you can explain why, you understand the underlying magnetic circuit rather than simply remembering an exam answer. These are the kinds of questions that are useful in oral examinations because the examiner can immediately tell whether the candidate understands the physical reason behind the answer. At this point, we can compress the first half of the course into one logical chain. MT requires a suitable ferromagnetic material. We establish a magnetic field. A discontinuity disturbs the magnetic flux. That disturbance produces flux leakage. Magnetic particles are attracted to the leakage field and form an indication. Everything else supports that chain. Current type controls how the field behaves and how deeply useful magnetization can extend. Field direction controls which discontinuity orientations are detectable. Particle properties control how effectively leakage is revealed. Lighting controls whether the inspector can see the indication. Bath concentration controls consistency. Equipment verification confirms that the intended magnetic field is actually being produced. The two-direction principle follows from the same physics. A single field direction can be blind to discontinuities that run approximately parallel to the field. Therefore, complementary magnetization directions are used. Finally, an indication must be evaluated against the applicable acceptance requirement. Detection and acceptance are different stages. If you remember this cause and effect chain, the detailed rules that follow will have a clear purpose rather than feeling like a collection of disconnected numbers. Safety in MT starts with recognizing that the equipment combines electrical power, magnetic fields, chemicals, UVA radiation, and sometimes large or heavy components. Personnel should follow the site procedure and wear the required eye and face protection, gloves, protective clothing, and other PPE. Jewelry should be removed where it could create a hazard. Ventilation is important, particularly when chemical products or petroleum-based vehicles are used. Electrical safety deserves special attention. Never move a component while direct inspection current is flowing. Poor contact can create arcing, which can damage the component and injure personnel. Prods should not be used where arc strikes are prohibited. The field tips also protect inspection quality. Start with a material check, clean the surface, and use two directions when appropriate. For fluorescent inspection, allow the full dark adaptation period before evaluating indications. Verify the bath before the shift and monitor UVA intensity because lamps degrade over time. One of the most useful field habits is to slow down before energizing the equipment. Check the component, check the technique, check the contacts or yoke, and check the surrounding area. A rushed setup is where both safety incidents and missed indications tend to begin. This slide closes the core MT theory and process section. The most important principle is that MT is a method for finding surface and near-surface discontinuities in suitable ferromagnetic material by detecting flux leakage. The inspector must control field direction, current type, particle condition, lighting, equipment performance, and examination sequence. The continuous technique normally provides the highest sensitivity, especially when the material has low retentivity. Field verification tools have specific purposes. The QQI can address field direction and strength, while other indicators provide more focused checks. Demagnetization is not an optional housekeeping step when residual magnetism could affect subsequent operations. The training values identify a residual field target below 3 Gauss. The closing quotation on the slide is worth taking seriously. The best inspector is not simply the person who finds the most indications. The professional objective is to establish a reliable examination process so that relevant discontinuities are not missed and non-relevant or false indications are not unnecessarily rejected. Now we move from the core method into calculations and practical technique selection, where the physics becomes numerical. The coil shot calculation is a practical example of how geometry affects magnetization. The key quantity is the length-to-diameter ratio, or L/D. Length is the effective length of the component being magnetized, and diameter is the relevant diameter. For a ratio between 2 and 15, the standard coil relationships can be applied as specified. If the ratio is below 2, the component may need ferromagnetic extensions to increase the effective magnetic length. If the ratio is above 15, the component is generally examined in sections. The training material gives 2 ampere-turn relationships. For a low L/D ratio between 2 and 4, Ni equals 45,000 divided by L/D. For a higher ratio above 4, Ni equals 35,000 divided by L/D. Consider the worked example. A steel bar is 20 inches long and 4 inches in diameter, giving an L/D ratio of 5. Because 5 is above 4, use the 35,000 relationship. That gives 7,000 ampere turns. If the coil has 5 turns, divide 7000 by 5 and the required current is 1400 amperes. The important lesson is to calculate the ratio first. Do not choose the formula from memory before checking the geometry. The prod technique requires control of spacing, current, coverage, and safety. The training material gives a general prod spacing range of 3 to 8 inches, or approximately 75 to 200 millimeters. Why does spacing matter? If the prods are too close, current density can become highly localized, increasing heating and arcing risk. If they are too far apart, the magnetic field between them may be insufficient for reliable detection. The general current guideline shown is 100 to 125 amperes per inch of prod spacing. For 6-inch spacing, that gives a range of 600 to 750 amperes. But current alone does not define coverage. Each prod position covers a region, and adjacent positions should overlap. The examination should also be repeated in a perpendicular direction so that the field is changed relative to possible discontinuities. Contact quality is essential. Clean contact points reduce resistance and the likelihood of arcing. Current should never be activated while the prods are being placed or removed. Most importantly, do not use prods where arc damage is unacceptable. Finished machined surfaces, many pressure-containing components, plated areas, and locations governed by arc strike restrictions require a different technique, commonly a yoke or another non-contact arrangement. An MT indication must first be classified before anyone decides whether the component is acceptable. A relevant indication is associated with a genuine discontinuity that may affect serviceability. Cracks, seams, laps, cold shuts, and certain weld discontinuities are examples. A non-relevant indication is produced by a legitimate magnetic leakage field, but the cause is geometry or a normal material condition rather than a harmful discontinuity. Sharp corners, holes, keyways, threads, splines, and material interfaces can all create these patterns. A false indication is different again. It is not produced by the flux leakage of a genuine discontinuity. It can result from magnetic writing, contaminated bath conditions, particle banding, poor handling, or other process problems. This classification matters because the response is different. A relevant indication is evaluated against acceptance criteria. A non-relevant indication is identified and distinguished. A false indication should be investigated and, when appropriate, removed or confirmed through cleaning, demagnetization, or re-examination. Magnetic writing is the classic exam example. If a particle pattern appears after accidental contact or handling, do not immediately call it a crack. First determine whether the pattern can be reproduced or removed through an appropriate corrective action. Good MT evaluation is therefore detective work. Establish the source of the indication before making an acceptance decision. Understanding common discontinuities helps the inspector interpret an MT pattern in context. Fatigue cracks are service-induced cracks associated with cyclic loading and stress concentration. They are often sharp and linear and can be highly significant on pressure equipment, shafts, and other cyclically loaded components. Seams are elongated surface or near-surface imperfections associated with wrought products such as bar or tube. Laps are folded over material created during forming and can also produce sharp linear patterns. Cold shuts occur in castings when two streams of liquid metal meet without completely fusing. Their location and smooth linear appearance can help distinguish them from other conditions. Grinding cracks are associated with excessive localized heat during grinding, often combined with rapid cooling. They can appear as networks or as cracks related to the grinding direction. Weld cracks include several mechanisms and locations, such as crater cracks, hot cracks, hydrogen-related cracks, and toe cracks. Their significance depends on the mechanism, location, size, orientation, and governing acceptance criteria. The inspector should not try to identify every metallurgical mechanism from the particle pattern alone. MT provides evidence of a discontinuity. Manufacturing history, service history, metallurgy, and complementary NDT may be needed to establish the exact cause. That distinction keeps the inspection technically honest while still allowing the inspector to recognize patterns that deserve immediate attention. Weld inspection is one of the most common field applications of MT, and the technique must be systematic. Begin by confirming that the weld and adjacent material are suitable for MT, remove spatter, slag, oil, scale, and other contamination that can interfere with particle movement or create misleading background. If visible particles are used on a dark surface, an approved contrast aid may be applied where permitted. The magnetizing field is then established in a direction selected to reveal the expected crack orientation. With a continuous technique, particles are applied while the field is active, and the surface is allowed to drain sufficiently for evaluation. A weld should not be inspected in only one direction. Rotate the field approximately 90 degrees and repeat the examination. This is particularly important because cracks can be longitudinal, transverse, or oriented at intermediate angles. Do not focus only on the weld crown. The heat-affected zone can also be susceptible to cracking. Weld geometry can create non-relevant particle accumulations, so the inspector must distinguish geometric effects from real discontinuities. After inspection, demagnetize where required, verify the residual field, and document relevant indications with location, dimensions, photographs or sketches as appropriate. Finally, use the actual acceptance code. AWSD 1.1, ASME requirements, API 1104, and other specifications have their own rules. Detection is performed by MT, acceptance is governed by the applicable requirement. The industrial applications of MT explain why the method is so important in oil and gas inspection. During pipeline construction, MT can be used on suitable ferromagnetic welds, tie-ins, repair areas, and selected components. In pressure vessels, attention is often directed toward shell welds, nozzle junctions, support attachments, and areas identified by service history or inspection planning. Rotating equipment provides another major application. Shafts, impellers, crankshafts, connecting rods, blade roots, and other highly stressed components can develop fatigue-related surface or near-surface cracking. Structural and lifting equipment also benefits from MT, hooks, rigging hardware, structural welds, lifting frames, and other ferromagnetic components can require examination because a relatively small crack can have serious consequences. The reason MT is attractive in shutdown environments is its combination of portability, speed, and immediate indication. A yoke and suitable particle system can be taken directly to a weld, and the inspector can evaluate the result without transporting a large component to a laboratory. But portability does not remove the need for engineering judgment. Every application still requires material suitability, correct field orientation, appropriate current, controlled particles and lighting, and acceptance against the governing specification. Selecting MT over another NDT method should always be based on the inspection objective. MT is particularly strong for surface and near-surface discontinuities in ferromagnetic materials. PT can provide excellent surface sensitivity on many non-porous materials, including non-ferromagnetic alloys, but it does not provide meaningful volumetric or near-surface capability in the same way. Ultrasonic testing is generally stronger for locating and sizing internal or deeper discontinuities. Radiography provides volumetric imaging but brings access, radiation safety, and exclusion zone considerations. Eddy current methods are highly portable and fast for conductive materials and can be effective for surface and near-surface flaws in suitable geometries. So the question is not, which method is best? It is, which method is capable of finding the expected discontinuity with the required reliability under the actual material and access conditions. For a ferromagnetic weld during an oil and gas shutdown, MT may be the fastest practical method for surface and near-surface crack detection. If the engineering concern is a deep internal flaw, MT alone is not sufficient. Professional NDT planning often uses complementary methods. One method may locate a surface crack, another may characterize depth, and engineering acceptance may require both results. Method selection is therefore a technical decision, not a preference for the inspector's favorite equipment. The common field mistakes on this slide are valuable because each one can produce a real inspection failure. The first is inspecting in only one direction. A field that is poorly oriented to a crack can miss it completely. The corrective action is to use complementary magnetization directions as required by the procedure. The second is selecting the wrong current type. Using AC for a deep near-surface concern can reduce the probability of detection because of the skin effect. Conversely, selecting a current with poor particle mobility can reduce the visibility of indications. The third is inadequate dark adaptation during fluorescent inspection. The inspector's eyes need time to adapt before subtle indications can be judged reliably. The fourth is incorrect bath concentration. Too little particle concentration can miss weak indications, too much can create background and mask them. The fifth is skipping demagnetization when it is required. Residual magnetism can interfere with welding and machining. The sixth is failing to re-inspect repaired areas. Grinding, welding, and other repair operations can introduce new discontinuities, so the repaired area becomes a new inspection target. These mistakes are not solved by more experience alone. They are best controlled through procedures, checklists, training, equipment verification, and disciplined execution. The first 5 Level 3 style questions combine calculation, technique selection, lighting, demagnetization, and magnetic properties. Question 1 uses the low L/D coil relationship. With a ratio of 3, the training formula gives 45,000 divided by 3, or 15,000 ampere turns. With a 4-turn coil, the required current is 3,750 amperes. Question 2 asks for the current type that combines strong particle mobility with near-surface capability. The training answer is half-wave rectified current because its pulsing effect provides excellent particle movement while avoiding the purely surface-limited behavior of AC. Question 3 presents a fluorescent inspection area at 35 lux. The training limit is 20 lux, so the area must be darkened before inspection continues. Increasing UVA intensity is not a substitute for controlling ambient white light. Question 4 gives a residual field of 4 Gauss after demagnetization. The training target is below 3 Gauss, so the component must be demagnetized again and rechecked. Question 5 asks about a low-retentivity component. Because it cannot hold sufficient magnetism after the field is removed, the continuous technique is required. When studying these questions, calculate first, compare against the specified limit second, and only then select the answer. The second group of questions moves further into field practice. For 5-inch prod spacing, the general guideline of 100 to 125 amperes per inch gives 500 to 625 amperes. This is a general training value, the governing procedure remains the controlling document. The accessory that verifies both magnetic field direction and strength is the QQI. A field indicator and a gaussmeter address field strength, while a pi gauge is primarily used to evaluate direction. The central bar conductor question is a classic conceptual trap. The conductor itself may be non-ferromagnetic, but current through it creates a circular magnetic field that magnetizes the surrounding ferromagnetic ring. The field type is determined by the current arrangement, not by the magnetic nature of the conductor. Fluorescence throughout the settling test liquid is a warning that the bath may be degraded or contain very fine suspended particles. It is not evidence of a perfectly conditioned bath. Finally, annealed low-carbon steel can still require demagnetization. AC coil treatment or controlled current reduction can be effective depending on the procedure. The common theme is that each answer comes from a physical principle. If you understand the principle, the exam question becomes much easier even when the wording changes. The answer key slide is most useful when we use it to confirm the reasoning rather than simply memorize the letters. For the coil calculation, the ratio of 3 places the component in the low L/D range, so the 45,000 relationship is used. The resulting ampere-turn requirement is divided by the number of turns to obtain the current. For half-wave, the key feature is the pulsed magnetic field and the resulting particle mobility. For fluorescent inspection, 35 lux exceeds the 20 lux limit in this training material, so the environment must be corrected. For demagnetization, 4 Gauss is above the specified target of less than 3 Gauss. The correct response is to repeat the demagnetization and verify the result. For low retentivity, the residual technique is unsuitable because the component cannot retain enough magnetism after the external field is removed. The broader lesson is important for Level 3 preparation. Never rely on the answer key alone. Recalculate numerical questions and explain the physical reason for conceptual questions. In a professional examination or oral interview, a candidate who can explain the reasoning is much stronger than one who has memorized the answer letter. These critical numbers are useful as a revision framework, but remember that values shown in training material must always be checked against the governing code, specification, procedure, and equipment requirements for the actual job. The residual field target shown here is less than 3 Gauss, or 0.3 millitesla. Fluorescent MT requires at least 1000 microwatts per square centimeter of UVA at the test surface, with ambient white light no higher than 20 lux. The eye should adapt to the dark for at least 5 minutes. The particle concentration values are 0.1 to 0.4 milliliters per 100 milliliters for fluorescent particles and 1.2 to 2.4 milliliters per 100 milliliters for visible particles. The optimal UVA wavelength highlighted is 365 nanometers. The training material also identifies a minimum particle drain period of 60 seconds in the applicable wet procedures, prod spacing of 3 to 8 inches, a general current guideline of 100 to 125 amperes per inch of prod spacing, and approximately 90 degrees between complementary inspection directions. A good memory technique is to group numbers by purpose. Lighting numbers belong together. Bath numbers belong together. Demagnetization values belong together. Technique spacing and current values belong together. And always distinguish a training value from a universal code requirement. This current selection guide is best understood as a decision tree. If the primary objective is surface discontinuity detection, easy demagnetization, and strong particle mobility, AC is an attractive choice. Its limitation is the skin effect, so it should not be selected when reliable subsurface detection is required. If the inspection requires surface and near-surface capability with maximum dry particle mobility in portable equipment, half-wave rectified current is highlighted. Its major limitation is poor demagnetization capability. If both surface and near-surface detection and controlled demagnetization are required, full-wave rectified current provides a more versatile solution. Three-phase full-wave systems are suited to large stationary benches where high capacity, versatility, and efficient power use justify the equipment. A battery-powered yoke can be valuable for field work where electrical supply is unavailable, but the available magnetizing capability is limited. The key decision questions remain the same: what discontinuity are we trying to detect? How deep might it be? What field direction is needed? What particle system is being used? Can the component retain magnetism? And what will the downstream process require after inspection? Use the current type to solve those problems, not as an isolated piece of equipment knowledge. The induction selector brings the field direction principle together with the equipment. A headshot is a direct technique and produces a circular field, making it suitable for longitudinal flaws in bars, shafts, and similar components. Prods and clamps also create circular magnetization in the area between the contacts, but they carry the additional risk of arcing. A portable yoke is an indirect technique and produces a longitudinal field. It is therefore useful for transverse cracks, especially on welds and plates where arc damage must be avoided. A rigid coil or coil shot produces a longitudinal field and is particularly useful for long components. The length-to-diameter relationship then becomes important when determining magnetizing current. A cable wrap can establish a longitudinal field around a large component in the field. A central bar conductor is an indirect arrangement that produces a circular field in the surrounding ferromagnetic component. This makes it particularly useful for ring gears, bearings, and hollow cylinders, including inspection of inner and outer surfaces where the configuration permits. The memory rule is straightforward: circular field finds longitudinal flaws, longitudinal field finds transverse flaws. Then choose the equipment that can safely and effectively create the required field. These interview questions test whether you can explain MT like an inspector rather than recite a textbook. If asked why two directions are required, explain the field geometry. Useful flux leakage is strongest when the magnetic field crosses the discontinuity approximately at right angles. A single field direction can therefore miss cracks that are poorly oriented to it. If asked why AC was selected for a weld, explain its surface concentration and particle mobility advantages. Then acknowledge that if the inspection objective includes near-surface flaws, half-wave or another suitable current may be more appropriate. If asked how you confirm demagnetization, explain the measurement and acceptance requirement. The training material uses a calibrated field meter and a residual field target below 3 Gauss. Retentivity and coercivity should be explained in plain engineering language. Retentivity is the magnetism remaining after the applied field is removed. Coercivity is the reverse magnetizing force needed to remove that residual magnetism. If a welder reports arc blow after MT, suspect residual magnetism and review the demagnetization process. Finally, explain the QQI as a verification tool for field direction and strength, rather than calling it simply a sensitivity gauge. A strong Level 3 candidate can explain the reason, the practical consequence, and the corrective action. Codes and standards define the framework within which MT is performed and accepted. The presentation identifies several important references, but the inspector must always verify the current edition and the exact document governing the job. ASME Section 5, Article 7 addresses magnetic particle examination requirements in applicable pressure equipment contexts. ASTM E1444 is a major practice reference for MT of ferromagnetic parts and addresses methodology and process controls. AWSD 1.1 is important for structural welding applications. API 510 and API 570 address in-service inspection of pressure vessels and piping, respectively, and can establish when MT is appropriate during inspection programs. ASNT TC 1A relates to employer-based qualification and certification practices, while ISO 9712 and PCN are associated with third-party personnel certification schemes. Do not make the common mistake of treating one standard as the acceptance code for every job. A procedure may invoke ASME Section 5 for examination technique while the component acceptance criteria come from a construction code, specification, drawing, or client requirement. The inspector's responsibility is to know which document controls which part of the inspection, personnel qualification, examination method, equipment and process control, or acceptance criteria. That separation is essential for technically defensible reports. This final technical summary brings the entire chapter back to the fundamentals. First, MT requires a suitable ferromagnetic material. Second, the component must be magnetized in a way that produces useful flux leakage from the discontinuity of interest. Third, particles must respond to that leakage under controlled surface, bath, and lighting conditions. AC is strongly surface-oriented because of the skin effect. Half-wave and full-wave rectified systems provide greater subsurface capability, depending on the equipment and procedure. Direct techniques such as head shots and prods produce circular fields, while coils and yokes normally establish longitudinal fields. A central bar conductor can establish circular magnetization in a surrounding component. Because one field direction can miss certain discontinuity orientations, complementary directions approximately 90 degrees apart are normally required. The continuous technique provides high sensitivity because the magnetizing field is present while particles are applied. Verification accessories, bath concentration, lighting, equipment output, and demagnetization complete the quality control system. The final acceptance decision is not based on the inspector's opinion of whether an indication looks bad. It is based on the applicable acceptance criteria. If you can explain that entire chain clearly, you have understood the method rather than simply memorized it.